Alright, let's start. Can all of you see the shared screen?
Yes, sir.
Okay. So we'll continue with friction. We will do some more problems on wedge friction, which is slightly complicated, especially when you have to construct a three-body diagram. Right, so let's start with the problem. A block of mass 150 kg is raised by a 10-degree wedge weighing 50 kgs under it, and by applying a horizontal force as shown in the figure. Taking coefficient of friction between the all surfaces of contact as 0.3, find what minimum force should be applied to raise the block. Again, you have to assume the impending motion, although it is said to raise the block, assume that it is an impending motion. So let's start by constructing the free body diagram. So the forces that will be, so let's do this. So how to mark the forces? So here we know that the direction of applied force is P. So the frictional force should be in the opposite to direction of P. Okay, so this will be the normal reaction, and this will be the frictional force here. And we will go, of course, when we are going to draw the actual free body diagram, we are going to number them N1, N2, etc. But just for getting the direction, this will be the normal reaction, this will be the frictional force. Okay? Because both these forces will try to oppose the direction of motion of this wedge. Okay? So the forces on the upper block will be equal and opposite. Okay? So this will be in this direction. These are on the block. But of course, one normal reaction on the vertical wall and a frictional force which will oppose the direction of the motion. Okay. So now let's separate each of these objects and construct the free body diagram one by one. Alright. So there will be a normal reaction. Let's call this as N1. This as F1, and R1 is the resultant of the normal and the frictional, which makes an angle phi with the normal. That we have already studied when we studied the laws of friction, cone of friction. And again, normal reaction here. Normal reaction, and so frictional force we have got because it is not sometimes easy to get direction of friction directly from this block. So that's why we did this exercise on the earlier slide. Okay, just to get the direction of the force. Now we are naming them because each of this quantity will be different. Okay, so this is the frictional force F2, and that is going to be mu N2, and the reaction, that is R2. That makes an angle again phi, because friction is constant on all the surfaces. Okay? And the angle of this wedge is given as 10 degrees. Okay, so angle of the wedge is 10 degrees. So this is 10 degrees. Right. So if I draw a vertical line, the normal will also make an angle of 10 degrees. I hope you are well versed with this technique of marking the angle. And so now let's see the finished free body diagram. Just put it on the screen. Alright, so this will be the finished free body diagram. Any questions regarding this? Of course, there will be one more force, that is the self weight of the block. It is 150 into 9.8. Any question regarding how to And now you can solve this problem by doing summation fx and summation fy, but I tend to avoid that method because that just creates too much calculations and there is a tendency to make a lot of mistakes. So in order to avoid that, now I use this method. Okay. Now phi is coefficient of friction is 0.3. So tan phi is nu, that is equal to 0.3. So phi is friction angle. Sometimes I write it as phi s. Same thing. Tan inverse of 0.3. Can somebody tell me what is that angle? Yes, anybody calculating?
16.69.
16.69, or I'm just going to round it up to 16.7 degrees. Okay. Now what I have done, I have reduced this, like how many forces are there? One N1, new N1, and 2, new N2, 4, and this self-weight 5. Okay. So I am going to reduce this 5-force system into a 3-force system so that I can apply the Lami's theorem. Okay. So N1 and new N1 will be replaced by R1, and N2
आपके बैकग्राउंड में बहुत
and new
आवाज आ
N2
रहा है.
will be replaced by R. Alright, and then I will construct a force diagram marking all the forces in the space. I will take a coordinate system, and of course when you are marking these forces, one thing you have to keep in mind is we are going to apply the Lami's theorem. So either all the forces should converge at this intersection point, or all the force should go away from the intersection. Okay. Don't mark one force in one going towards the point of intersection and another force going away. So that will create error. Okay. So I will just mark these 3 forces. So first force will be R1. R1, from here I will get the angle, it makes an angle of phi. So I am just going to directly mark the angle here, 16.7 degrees. Then the self weight, so that is equal to 150 into 9.81, and R2 parallel to this force R2. Right, just to make it parallel, this is by R1, this is R2. Okay. So angle of the wedge is 10 degrees, this phi is 16.7 degrees, so total angle will be 26.7 degrees. Right. So now I have all the angles. Now I am going to apply the Lami's theorem. I don't really need R1. All I need is R2. So I am just going to apply Lami's theorem to R2 and this 150 into 9.8. Okay. So R2
Background.
divided by sine of the angle opposite to it. So that is this angle. It is slightly different color. So that is this angle, and that angle will be 90 minus 16.7 degrees. So sine of 90 minus 16.7 is equal to 150 into 9.81 divided by sine of the angle which is opposite to it, sine of angle which is opposite to this 150 degree force, that will be this total angle, this complete angle, and that angle will be this 90 plus 16.7 plus 26.7. So this whole angle. So this will be sine of 90 plus 16.7
Sir, there's some disturbance.
Pardon?
There seems to be some disturbance.
I'm not. Your voice is coming very low. Can you just speak a little louder?
Sir, there's some disturbance in the background.
Okay, okay, okay. It's probably because of the ceiling fan has this. Better now? Alright, so tell me the value of R2. Yes, R2 is
Sir, I'm getting 1939.84 Newton.
correct. 1939.84
84
newtons. Okay, right. Okay, R2 is 1939.84 newtons. Alright, so now let's do the calculation for P. So you have R2 over here, that is norm, and so that makes an angle. So just construct a vertical line. This R2 will make an angle of 26.7 degrees. All right, so that is I have got this from here. Okay, it is this is 26.7 degrees. So R2 is actually, I just extended the line of action and it is equal and opposite, and if I construct a vertical line, so this will be the opposite angle, so this also will be 26.7 degrees. So R2 is 26.7 degree, making an angle with the vertical, and there will be, then there will be self weight of the wedge, that is 50 into 9.81, and there will be a normal reaction, let's call that as N3 and new N3. Finished free body diagram, so this is the free body diagram. Okay. So now here now you can directly apply the summation fx summation fy, because here you have to just resolve one force and other forces are already there. So let's do summation fy equal to 0, so upwards positive, so n3 minus this vertical component of 1939.84 cos 26.7 minus 50 into 9.81, that is N3, and summation fx, so that will give you N3, so 0, so find out N3, and summation fx is equal to 0, so right hand side positive So new N3 plus 1939.84 sine 26.7 minus P is equal to 0. Find out the value of N3 first and then substitute it in this equation and find out the value of P. Tell me the value of N3 and then tell me the value of P also. Yes?
Triple to 3.49.
Triple
To
two
3.4.
3.5. Oh, yeah, 49 or I rounded up to 5. And P is
3095.
no new N3 it is into new. This is 0.3. 0.3 into this, that is approximately 600 plus this will be sine half of that, so 900. 900 plus 600, it should be around 1500.
One five three eight.
Correct, 1538.66 newtons. All right, okay, so that's the value. Okay, next question. To level a wood deck, wood wedges A and B are placed under the corner of the deck. Okay, A and B are two wedges. The wedge B is rests on the wood board as shown, and a bar clamp is used to apply equal and opposite forces to the wedges. So these are equal and opposite forces, okay, P and minus P. Knowing that theta is equal to 18 degrees and the coefficient of static friction between all wood surfaces is 0.35 and zero point 0.6 between the board and the ground. So down here the coefficient of friction is not same. Here it is 0.6 between the board and the ground, and between all the wooden surface everywhere else it is 0.35. Okay. So we have to determine the magnitude of P of the clamping force for which the upward motion of the deck is just impending. Okay, so that this block is just about to move. All right. So now let's analyze this. So the horizontal forces are equal. Vertical, it should be horizontal actually, and they are opposite. Nu static of the ground is greater than nu static of the wood. Okay. Now, when you are solving that, assume you cannot assume impending motion of the board. Here, there is no impending motion, okay? And then there will be slip at the wood and wood contact. So all the wooden surfaces will be, there you have to assume the impending motion. Okay, and nu static is tan inverse of 0.35, and that is equal to 19.29 degrees. Now let's solve this by drawing the free body diagram one by one. So first let's consider the top wedge. Right, so here there will be so there is no weight given for the what you say the deck. So and it is all given as 8 kilonewtons. So we are going to assume that the total weight which is acting on the top of the wedge is 8 kilonewtons. This will be the frictional force F, and this as R1, and this is the phi static, which we already calculated on the earlier page. Phi static is tan inverse of nu static, that is 0.35, that is 19.290. Okay, so I will just construct a triangle for this forces. So this will be F and R. The force triangle. So F, this is 8 kilonewton, and R1, this is phi s. So cos phi s is equal to 8 divided by R1. So find out R1. Yes, how much is R1?
8.4.
8.47 kilonewtons. Okay. Similarly, there will be reaction over here also. So this will be, now I am directly replacing the, so this is the normal to the inclined surface, and F2 and N2 I am directly replacing it by R2. R2, and this is phi s. Okay, and this angle is 18 degrees. So now let's apply, let's go to the next slide and see the diagram. P, R1, R2. And now let's write the Lami's equation. So Lami's equation, this will be, if I just construct this three forces together, this will be P and vertical line and R1 and this will be R2. This makes an angle. This is phi s, also phi s, and this is 18 degrees. All right. So now let's apply the Lami's theorem. So R1 divided by sine, just a slightly different color. So this total angle, so that will be 90 plus 80 plus phi s is equal to R2 divided by sine this total angle 90 plus phi s, and that is equal to P divided by sine 180. So this angle, and that angle is 180 degrees minus phi s minus phi s. All right. So find out P, because R1 we already know. We don't need to go into R2. We do not need this. So directly find out using this first and the last part of the equation. Find out P. Phi s we have already determined that is 19.29 degrees. Yes, how much is P? Anybody? Is anybody calculating?
Sir, 8.891.
Correct. P is equal to 8.891 kilonewtons. So that is the value of P. All right. Now we have solved for this, and now we have to check whether the motion is impending at the board and the ground, this interface. Okay. Or in other words, I have to check whether the frictional resistance offered by the interacting surface of the board and the ground is more than the frictional force which is generated, that is Fg. All right. So let's do that real quickly. So 8, this is a normal reaction. So F1 is equal to nu into 8. That is normal reaction. All right. So F1 is equal to nu into 8 kilonewtons. So that is equal to 0.35 into 8. So that is equal to 2.8 kilonewtons. Okay. Now let's do summation Fy. Summation Fy is equal to 0, upwards positive. So again Ng minus 8. Now I have not separated any of these blocks. I have taken the entire thing together, the two wedges and the board, everything I have taken it together. So there are no interacting forces between the surfaces, all the wooden surfaces. So Ng minus 8 kilonewton is equal to 0. So, 0. So Ng, normal reaction, is 8 kilonewtons. Ng is 8 kilonewtons. So now Fg max, that is the maximum frictional resistance offered by the ground will be equal to nu ground into Ng. Alright, so that is equal to 0.6 into 8, so that is equal to 4.8 kilonewtons. So that is the maximum frictional resistance. Okay. Now find out the frictional resistance, frictional force which is generated, that is Fg. So to find Fg, just do summation Fx is equal to 0, right hand side positive. So Fg minus F1 is equal to 0. So Fg is equal to F1. Fg is equal to F1 is equal to 0.35 into 8. So that is equal to 2.8 kilonewtons. Okay. So the frictional force which is generated is 2.8 kilonewtons, which is less than the frictional maximum frictional resistance offered, that is 4.8 kilonewtons. So so we are okay. All right. So P is equal to 8.892 kilonewton. This is okay because the motion is still the system is not moving when these forces are generated. All right. Any questions? Can I go to the next one? Okay. Next question. Two wedges of 8 degree, two 8 degree wedges of negligible weight are used to move and position a 530 Newton block. Knowing that the coefficient of static friction is 0.4 at all surfaces of contact, determine the magnitude of force P for which the motion of the block is impending. So you have to find out this value of P for which the block is impending. Now they have, in this case, they have already marked the angle 20 degrees. In question, you cannot expect that. So now let's do some analysis. So where is the slip impending between the wedge and the block? Between these two wedges. Alright, so wedge and the block, and between the block and the inclined surface. So all these surfaces, the motion is impending, and the static friction is 0.4. So the friction angle everywhere is tan inverse of nu s. So that is equal to 21.801 degrees. All right. Now let's consider the free body diagram of the block first. So what are the forces acting on this? So first, so I'm going to assume that this is okay. So this is how weight is passing through the center of this block. I'm going to assume, and that weight is 530 newtons. And then there is this reaction R2, and R2 makes an angle of pi s, which we already calculated. Pi static, and R1 also makes an angle of phi s. Okay, and phi s we have already calculated as 21.801 degrees. Right. So now if I construct the, so I've again reduced the system into a 3-4 system. So a vertical force 530 newtons, (530 newtons) acting downwards, and this is this force R2, and R2 will, so this is 21.801 degrees. So R2 will make an angle of this plus 90 plus this total angle. Right, so it will make an angle of 21, so 90 plus total angle, this total angle will be 90 plus 21.801 plus 21.801. So total angle will be between R2 and R1 will be, this angle will be 90, this angle 90 plus this phi s and this another phi s. So 90 plus 21.801 plus 21.801. So find out how much that is. Okay. And this remaining angle will be that is this angle. So that will be 180 minus 20 minus 5s. Alright, so that will be 180 minus 90 minus 5s. So calculate all these angles and tell me the values. So any questions, please ask. Huh? It's a slightly complicated problem. 180 minus 20 minus pi. Yes, are you calculating? Hello? Hello? Okay, so these are the angles. I don't know whether you have got it correctly. And R2 makes an angle of 21.801 minus 28 degrees. Okay, so that is equal. This small angle is 1.801 degrees that you will need while marking the angle on the other block. Okay, so this also will be 1.801 for the equal and opposite R. Okay, now let's apply the Lamis theorem. So we have got all the angles. Now apply the Lamis theorem. So R1 divided by sine 88.2 is equal to R2 divided by sine 138.2 is equal to 530 divided by sine 133.6. Okay, so find out R1 and R2.
Sir, R1 is 731.50.
Yes, R1 is
731.50.
R2 is
487.
487.82.
37.8. Alright, now let's draw the free body diagram of the first wedge, that is this wedge. Okay, this wedge. Okay. So all the interacting forces will be equal and opposite. So this wedge is placed over here like this. Okay, it is like this. So we are going to construct the free body diagram for this wedge. So this R2 is making an angle of 1.801 with the horizontal. So when we are drawing the free body diagram of this wedge, we are going to take that equal and opposite, and it makes an angle of 1.801 with the horizontal. Okay. So let's go to that wedge diagram, and one by one let's mark the forces. So R2 this makes an angle of 1.801 0 1 and draw a normal to this inclined surface and R3 will make an angle of that is tan inverse of nu s, so that is equal to tan inverse of mu s that is equal to 21.801 degrees, and of course this angle, wedge of the angle is 8 degrees. Okay, so this angle made by the normal also will be 8 degrees. So we have got all the angles, and this is R2 and this normal force will be P. Alright, so we have got all the angles now, and we have got all the forces. Now the total force will be okay, so this is R3, R2 and P. Okay, so now let's construct the Lami's diagram. So this is P, all the three forces are intersecting, so this is P and this is this total angle will be 90 plus 20 plus 1.801. So 110 plus 1.801, so that is total is 111.801, and this this angle, this total angle this will be 90 plus 8 plus 21.80. This angle will be 180 minus 8 minus 21.801 minus 20 minus 1.801. So calculate these angles. Tell me the values one by one.
Sir, angle between P and R3 is 119.8.
Correct, 109.801. And this angle?
128.398.
Correct. 128.39. Okay, so these are all the forces and the final angles I have calculated. Okay, now let's apply the Lami's theorem. So we know R1 and R2. So from this we know R2. So our aim is to find P. So let's apply the Lami's theorem. So R2 divided by sine 119.801 is equal to R3 divided by sine 111.801 111.801 is equal to P divided by sine 128.398. Find
Sir, P is 440.57.
correct, 440.574. All right. So we have solved a variety of examples from simple to complicated. I hope you have a good handle on how to construct the free body diagram, especially for wedge friction. So that's all for today. If you have any questions, you can ask before we end the lecture. I have already uploaded all the notes for the friction chapter in the class materials folder. I hope you are able to find it. Alright, if there are no more questions, then we can end it. I will upload the friction assignment today that you can submit it after your term test. Next week you have your term test, and I hope you know that it is going to be offline. All the best for that. And I think next week you might lectures also might be starting offline. All right, that's it. Thank you. All right, thank you. Bye. You can go to the next lecture.